In Lecture 19, we're continuing to talk about trigonometric identities, and in this section we're going to practice and do several versions of proofs of these identities. In other words, we want to establish those identities. We want to prove that they are in fact true. Now this phrase, establish the identity, means that you're going to start with one side of a given equation and using the appropriate basic identities and algebraic manipulations arrive at the other side. In many cases, which side to start with is up to you, and we'll talk about different examples of why I choose one side versus the other. Now, keep in mind that this is really at the heart of what mathematics is all about. We're moving from procedural mathematics, where you just repeat what the instructor does in class, to more abstract understanding of mathematics, which is verifying or proving the theorems that we use in class. And the only way to really get good at this is practice. And practice requires time and effort. And you've got to come at this with a spirit of willingness to try lots of different things until you finally arrive at the correct proof. Now these drops coming off of these guys, these aren't tears of weeping, these are sweat of the brow, so you are demonstrating that it's going to take some work to be able to accomplish the skill of establishing trigonometric identities. So when you come across a problem that says establish the identity, keep in mind you're trying to take one side of the equation and turn it into the other. So one of the best strategies for deciding which side to start with is which one looks the messiest, and can I simplify it using one of the strategies we talked about in the previous lecture. For example, in this case, which side looks most complicated? Well, clearly the side on the left, cosecant of theta times tangent of theta, has more functions in it, and because they're not all sines and cosines, one natural approach would be to let's convert everything from their current form into sines and cosines. So let's start with cosecant of theta times tangent of theta. Again, we're starting with one side, replacing things with their identities that we know from basic identities, and we're doing algebraic manipulations to try to end up with secant of theta. We want to show that this eventually turns into secant of theta. So I'm going to write it in this way. I'm going to start with one side. I'm going to say, what is that equal to? Well, it is equal to something based on our knowledge of basic trig identities. It's equal to 1 over the sine of theta times the sine of theta over the cosine of theta. Now, why is that true? It's true because cosecant of theta is 1 over sine theta, and tangent of theta is sine of theta over cosine theta. You need to be able to explain, although I'm not making you write it down, but you need to just understand why it is each line that I write is a true statement. Now, this then is equal to 1 over cosine of theta, because via algebra I can cancel the signs from the top and bottom. And lastly, what is 1 over cosine of theta? And keep in mind, what am I trying to get to? I'm trying to get to secant. Well, I'm there, right? Because 1 over cosine of theta is secant of theta. I have finished my proof. So I write a little box at the bottom saying proved. That's what the little box means. I've done it. I'm complete. That is a complete proof. In this example, we're asked to show that the sine squared of negative theta plus cosine squared of negative theta is equal to 1. So the obvious side to start with would be the left-hand side. So sine squared of negative theta equals, not equals, sorry, plus cosine squared of negative theta. Now, what is that equal to? Well, you can do this a couple of different ways. Let's recognize the fact that you've got the negative inside the parentheses of the functions, which means it would be natural to go back to one of our basic identities for even odd properties, right? We know that with sine, I'm going to just come over here with a thought bubble. Sine of negative theta is negative sine of theta, correct? And cosine of negative theta is simply cosine of theta. Now you also have to remember what the squared in here means. Just want to make sure you recall that that means you're squaring the whole function. So this is really like sine of negative theta squared plus cosine of negative theta squared. Now all I did was rewrite what square means. When you say sine squared, it means the sine of the function squared. Now this right here says I can pull the negative sign out front of the sine. So this is like negative sine of theta squared plus, and then with the negative sign on the cosine, it just disappears. So you have cosine of theta squared. So the second guy is simply cosine squared of theta, because that's what it means to write cosine of theta quantity squared is the same thing as writing cosine squared of theta. Now what happens when you square a negative sign? Right? Negative times a negative equals a positive. So this is the same thing as positive sine squared of theta. And now we know by trigonometric identities that sine squared plus cosine squared is always equal to 1. Proved. Alright, let's give this one a shot. We have sine squared of negative theta minus cosine squared of negative theta, all divided by sine of negative theta minus cosine of negative theta. We want to show that that is simply equal to cosine of theta minus sine of theta. So we can do some of what we did on the previous example with what we did on top. If I have sine squared of negative theta minus cosine squared of negative theta divided by sine of negative theta minus cosine of negative theta, I can use the even-odd properties for trig functions. On the top, remember I have sine of negative theta squared minus cosine of negative theta squared. And on bottom, all I did was rewrite, on top, all I did was rewrite the square using what it actually means, to say sine squared is sine of negative theta squared. On bottom, I'm going to go ahead and apply the even-odd function properties. So I can pull the negative sign out of sine of negative theta and get negative sine of theta. But for cosine, which is even, the negative sign just drops out. So I have cosine of negative theta. Of positive theta on bottom, like this. And now applying the even-odd properties on top, I've got a negative sign that's going to come out front, so I end up with a negative sine of theta squared minus, and then that one just drops out from inside the cosine of theta squared, divided by negative sine of theta minus cosine of theta. Alright, which looks like this. It's you square a negative, you get a positive, so you have sine squared of theta minus cosine squared of theta over negative sine of theta minus cosine of theta. Now I've got rid of all these negatives inside, but I still haven't got to what I'm looking for. So what else might I try? What seems a natural thing to try next is, because you've got, again, a difference of squares, we can try factoring. And let's factor the top. If we know we have a difference of squares, sine squared of theta minus cosine squared of theta, that would be like a plus b times a minus b, or sine of theta minus cosine of theta times sine of theta plus cosine of theta. Again, where a is simply sine of theta, b is cosine of theta, so you have a plus b times a minus b. That's where I got this. Actually, I did a minus b, a plus b, but that doesn't make a lick of difference. Minus cosine. And on bottom, let's factor it too. You notice they both have a negative, so let's pull a negative 1 out on bottom. You're left with sine of theta plus cosine of theta when you pull a minus sign out of both of them. And the beauty of doing that is now you see sine of theta plus cosine of theta on top and bottom, divided by negative 1, which is the same thing as multiplying by negative 1. Divided by negative 1 is the same as multiplying by negative 1. Hope you can see all of my parentheses there. So this, if you distribute the minus sign, you get cosine of theta minus sine of theta. Actually, you get a negative sine of theta plus cosine of theta, which I can rewrite as cosine of theta minus sine of theta, which is exactly what I'm going for. And voila, I finished the proof. So in this example, we see the more complicated side is the first side. So let's start with 1 plus tangent of u over 1 plus cotangent of u. And I suggest that we try our sine cosine trick. Let's change everything into sines and cosines. So 1 plus sine of u over cosine of u divided by 1 plus cosine of u over sine of u. Now if we use common denominators, we can simplify the numerator, and denominator. So on top, the common denominator would be cosine of u. So this becomes, if I multiply by cosine of u over cosine of u, I end up with cosine of u plus sine of u over cosine of u. And on bottom, if I treat this as sine of u over sine of u, I end up with sine of u plus cosine of u over sine of u. And now using algebra, we invert and multiply. So this looks like cosine of u plus sine of u divided by cosine of u times the reciprocal of the denominator, sine of u over sine of u plus cosine of u. And you'll notice cosine u plus sine u is the same thing as sine u plus cosine u, so these cancel. And you end up with sine of u over cosine of u. But look what we're trying to get to, tangent of u. So is that tangent of u? In fact, it is, right? Because we know that sine over cosine is always tangent, and we've proven it. In this example, I think it's clear we're going to start with the left-hand side. We have already the left-hand side in terms of sine and cosine. What makes natural sense here is because we have two fractions. Let's add the fractions together by finding a common denominator. The common denominator for this will be the product of the two denominators, which is 1 plus cosine of theta times sine of theta. So we'll start with the first fraction, sine of theta over 1 plus cosine theta. It's missing a sine of theta, so I'm going to multiply it by sine of theta over sine of theta. Now it has the common denominator, plus 1 plus cosine of theta divided by sine of theta. We're going to multiply it by 1 plus cosine of theta, 1 plus cosine of theta on top and bottom. Okay, so this will equal, everything has a, now over the common denominator, which is 1 plus cosine of theta times sine of theta. I have a sine squared of theta from the first fraction, and the second one, if I multiply 1 plus cosine of theta times 1 plus cosine of theta and FOIL, I'll get 1 plus 2 cosine of theta from the outside and the inside added together plus cosine squared of theta. Okay. Alright, now let's see what can I do to simplify that. recognize that I have this on top. Sine squared of theta plus cosine squared of theta always adds together to be 1, so this leaves behind a plus 1. Combine that with the other plus 1, and I've got 2 plus 2 cosine of theta over 1 plus cosine of theta times sine of theta. Alright, now what I notice next is that in order to make the numerator look more like the denominator, or at least to get a common factor that will cancel, I could factor out a 2, which leaves behind a 1 plus cosine theta divided by 1 plus cosine theta sine theta. These are both multiplied across the top and bottom, so I end up with 2 over sine of theta. And if you think about where we're trying to get to, this is clearly 2 times 1 over sine of theta, which is 2 cosecant of theta. Proved. Alright, looking at a look at tangent of v plus cotangent of v over secant v cosecant v. We want to show that that is always equal to 1 for every value of v. So we'll start with the left-hand side because it is the more complicated. I think it's natural then to apply our strategy where we change everything into sines and cosines. So this becomes sine of v over cosine of v, where there was a tangent, plus cosine of v over sine of v, where there was a cotangent. Secant of v is 1 over cosine of v times cosecant, which is 1 over sine of v. Okay? I think we should combine the numerator into a single fraction, so the LCD on top would be cosine of v sine of v, so I need to multiply by sine of v over sine of v here, and cosine of v over cosine of v here, which gives me a, this is all in the numerator, it's all over cosine v sine v of sine squared v plus cosine squared v on top. And on bottom, if we multiply 1 over cosine of v times 1 over sine of v, you get 1 over cosine v sine of v, which we can now invert and multiply and end up with sine squared of v plus cosine squared of v over cosine v sine of v from the numerator times cosine of v sine of v over 1. And the cosine v sine v cancel, and we remember that sine squared plus cosine squared is always 1, so we end up with 1 over 1, which is 1 done. In this example, we're given 1 minus sine of theta over cosine theta is equal to cosine of theta over 1 plus sine of theta. And generally, we'll start with the more complicated side, but when that's not obvious, we should start with whatever side we think might work. In this case, I can do this on either side, but I recall one of my previous suggestions from lecture 18, which is where we could multiply by the conjugate of the denominator. So I'm going to start with cosine of theta over 1 plus sine of theta. And I'm going to try to get it to look like the left-hand side by multiplying by 1 minus sine theta over 1 minus sine theta. Just to see what happens when we multiply by the conjugate of the denominator. On bottom, because it's a plus b times a minus b, you get the difference of squares. If you FOIL it out, the middle terms cancel. You end up with 1 minus sine squared theta. And on top, we end up with cosine of theta times 1 minus sine theta. The denominator will factor. Actually, we don't have to factor that. We just remember that if we have sine squared of theta plus cosine squared of theta. Oh, you can't read that when I write it off the screen. Sine squared theta plus cosine squared of theta equals 1 means that 1 minus sine squared, which is what you get if you move this to the other side, is simply cosine squared. So on bottom I can write this as cosine squared of theta, and on top I have cosine of theta times 1 minus sine theta. Alright, and I don't think that's at all what I wanted to do. Because that doesn't give me where I'm going, does it? Yeah, it does. Pfft. Sorry, I forget which direction I was going. I want to get to this guy, right? So, sorry about all that brain lapse that I had there. Neurons misfiring. One of these cancels with this guy, and I'm left with 1 minus sine of theta, and I'm done. Thank you very much. Voila. Proved that is 1 minus sine of theta over cosine of theta. Okay? So, multiplying by the conjugate of the denominator was the trick. You actually could have started with the left-hand side and gone to the right-hand side, multiplying by the conjugate of the numerator instead, and you would have still been able to prove this identity. So just to summarize some of the tips that you pick up along the way as we talked through this lecture, just some guidelines. It's always preferable to start with the side containing more complicated expressions. And if you have things involving functions other than sines and cosines, it might be helpful to rewrite those using the quotient identities. If you have fractions involved, and that's what number 2 here says, you might want to rewrite those sums or differences as a single quotient by combining those fractions. Sometimes rewriting those things in terms of sine and cosine, like I was saying earlier, is always going to provide some help. And keep your end goal in mind.